With E2 reactions, we'll need to think about stereospecificity. So this is what kind of alkene it is going to form. In an E2 reaction, we need to have a bromine and a hydrogen that are anti-coplanar. So the elimination is going to happen right there. So we have bromine that needs to be in the same plane with hydrogen so that they're lined up and they can see each other and they can eliminate. The product of that would be so this methyl and the tert-butyl are going to be on the same side, and the phenyl and the hydrogen will be on the same side because they were on the same side of the reaction here. The double bond that forms is here. So this would be the product of that reaction. And when the bromine is on the opposite side of the hydrogen, this is anti-coplanar. And that usually results in the E isomer. If we were to determine this, this is my large group, this is here, that is E. So if I took this compound here, rotated it around the C bond, so I'm just going to rotate this here, so that the Br and the H are on the same side. So they're all in the plane because they're all in the lines without the wedges and dashes, and H and Br are in the same plane. This is syn coplanar. You can't do an E2 elimination when it's syn coplanar. So the beta hydrogen has to be anti-coplanar to the leaving group in order to do an E2 elimination. And this is explained by your favorite Newman projections. If we look at that last compound, we had the methyl and the phenyl on the front carbon, and then there's H here. This is the anti-coplanar when it is staggered. So our base would come in and grab that hydrogen, and it would form the double bond there while that is getting kicked off. Sterically, the base is not in the way of the bromine. It can just grab the hydrogen easily, and the bromine leaves on the other side. If they're syn coplanar, this is very high energy. It's eclipsed, and the base is going to have a hard time coming in because this electron cloud is going to be repulsed by the bromine electron cloud. And then just a note here, the phenyl group is pH. So if it's syn coplanar, they're going to be eclipsed. It's going to have high energy to get even into that conformation, so you won't see that elimination happen. But when it's anti-coplanar, the base can come in, grabs the hydrogen, and you eliminate that. So your Newman projection looks like this. So we get that alkene. If we're looking at this reaction, my bromine and the hydrogen are anti-coplanar. So then when I do the elimination, the R's are going to be on the same side of the double bond, the R1s anyway, and the R2, since they're both dashed, will be on the same side of the double bond as well. And that one is here, and the same thing here. This is anti-coplanar. Now the R1 and the R2 on this side are both wedged. So these will be on the same side of the double bond. And then the R2 and the R1 over here. And that forms the alkene. If you're doing the E2 elimination in a ring system, we need to have the leaving group on the opposite face of the beta hydrogen. So here I have HA and HB. Chlorine is my leaving group, and that is wedged, and the HBs are both dashed. So we can do an elimination of HB or HA. If I do HB, I get this one. So this is from HB. And this is from taking HA. So this is the major product because it forms a more stable alkene. This would be the minor product because we have a disubstituted alkene instead of the trisubstituted alkene. The other thing with this one, when we eliminate it here, the stereochemistry is lost because alkenes are planar, and when we eliminated HA, this one stays the same because the reaction is not occurring over there. In this reaction, the chlorine is still wedged, but the hydrogens are wedged also, so this is going to be a no reaction. And that is because there's no hydrogens that are on the opposite face, so it can't do that elimination. So when looking at the major products and minor products for this E2 reaction, we're going to look at the substrates with a strong base. If I look at the first example, we have a base. And I'm going to look at the protons that are available. On this carbon here, there are no hydrogens. So we can't do an elimination that way. There's a hydrogen here, and there is a hydrogen there. The base is going to take the one that is opposite sides of the chlorine, which is the dashed one. And then we form the double bond there. That will be the major product. This could also rotate around so that this other hydrogen here faces back. Then we would get the Z isomer. For this here, our hydrogen that is available, again, there's no hydrogens available here. The hydrogen available is on the same side, so we're going to have to do a bond rotation. I'm going to redraw this. All I've done is I've just kind of rotated this about 30 degrees so that this line is flat. And then I added the missing hydrogens in. We can see here the chlorine is on the same side as the hydrogen, so we're going to have to do a bond rotation. So I'm actually just going to rotate this bond here to put the chlorine in the plane. So that becomes in the plane. Everything else here stays the same. And then when I move this into the plane, that's going to shift everything one position. So the tert-butyl group will now be pointing back, and then the hydrogen is coming forward. My hydrogen still is not the right spot. We want it to be in the plane or anticoplanar with the chlorine. So I'm going to rotate on this side, and I'm just going to rotate everything down one position. This side stays the same. And then the hydrogen now becomes in the plane. The methyl group that was back becomes forward. Ethyl group is back. Now we add our base. This is now anticoplanar. So it grabs the hydrogen, these bonds go here, and that leaving group leaves. And the tert-butyl group is here on the same side as the ethyl. And then we have a methyl group here. So that is our product. The E1 mechanism is a two-step process, just like in the SN1 mechanism. E1 stands for elimination and unimolecular. So what mechanism arrows you see here is just like the SN1. The first step is the same. We have loss of leaving group. And then the base can come and grab the proton after the carbocation is formed and eliminate the hydrogen. This is a proton transfer. It is a two-step reaction, and the rate determining step is the loss of the leaving group, just as it was in SN1. The substrate reactivity is also the same as in SN1. So this is the most reactive, and this is the least. And that is because we're going through the same carbocation intermediate. The rate determining step is loss of the leaving group and forming the carbocation. If it can't form, then the reaction is not going to proceed. We have loss of a leaving group, then we form the carbocation intermediate just as we did before. If we had a nucleophile, that would result in a substitution. if you have a base, that results in an elimination. Because E1 and SN1 proceed by the same first step, the competition generally results in a mixture of products. So you won't get nucleophilic substitution only or elimination only. You end up with a mixture of products. We've seen already that OH is a bad leaving group. But if we protonate it and make it a water, this is an excellent leaving group. We can do reactions with tertiary alcohols using concentrated sulfuric acid. We get water and the alkene. So the concentrated sulfuric acid is going to protonate that alcohol, and then you heat it, and that will drive the reaction to form the alkene. If you do this reaction with concentrated sulfuric acid, we can get a mixture of alkenes just like we did with E2. We get the Zaitsev, and this is the Hoffman. And this happens to be 90% Zaitsev, 10% Hoffman. And E1 reactions generally will produce the Zaitsev product because it wants to have the more stable alkene. In the last step of the mechanism, a proton is removed from a beta carbon that's next to the sp2 hybridized carbocation. So this would, we protonate the alcohol. That will leave, and you can form two products here. This would be the E or the Z. The E is preferred. So what would the product be for this reaction? You have loss of leaving group. We form the carbocation, and because we're forming a carbocation, a rearrangement is possible. In this case, it can happen and will to form the tertiary carbocations. This is a rearrangement. Now we can take our proton from HA or HB. If I take HA, double bond forms there. This is a tri-substituted. If I pull it from there, the HB, this is also tri-substituted. You may get a mixture of products here. This one might be preferred just because the double bond is in the ring, which is more stable than the other one. This would be major. That is the gist of the E1 mechanism. There is a lot less to worry about with E1 than there is with E2. Again, it just goes to the carbocation, so you have to remember that a rearrangement is possible, and you can have the elimination that will form the most substituted alkene or the most stable one.